Okay. Doing these a little more slowly. These are from a practice test. We want the augmented matrix that represents this equation, okay? Which states that a linear combination of V1, V2, and V3 is equal to the vector W, where V1 is the vector 1, 0, negative 2, V2 is the vector 3, 2, 0, V3 is the vector negative 2, 0, 5, and W is the vector 3, negative 8, 22. So there's V1, V2, V3, and W. Okay, now why is the augmented matrix? Because we asked to write the augmented matrix and reduce it to see if this equation has a non-trivial solution, a solution for which C1, C2, and C3 are not all 0. Well, we could write this out as an equation. We could write C1 times 1, 0, negative 2, plus C2 times the 3, 2, 0 vector, etc. That would be equivalent to the matrix equation, where the first matrix is the V1, the matrix with the V1, V2, and V3 vectors as columns, times C1, C2, C3 equal to the W vector. If you write out those equations in detail, and then write that as a matrix equation, you'll see that that's the way it works out. Okay, well, the matrix equation then is just replacing these V1, V2, and V3 with the column vectors. Matrix equation is going to be this. And this matrix equation is represented by this augmented matrix. Now we can reduce the augmented matrix and solve to see if we have a set of consistent solutions, if the equations are consistent, and if so, do we have solutions? And if we have solutions, do we have any free variables? So those are the questions that we would want to answer in interpreting the solution to the augmented, represented by the augmented matrix, represented by the reduced augmented matrix. Now, another thing we could do, of course, is we could, first of all, identify the fact that the determinant of this matrix is non-zero. We just expand along this row. The only non-zero cofactor that we would have would be the 2 times the matrix that we get from these elements, and that would, the determinant of this matrix we easily find to be 18. It's not 0, so that we do have a unique solution for C1, C2, and C3. In other words, these 3 vectors can be combined to give us this vector, this W vector. Now, the problem specifically asks you to do this with the augmented matrix, but I wanted to expand that a little bit by showing you that we could also determine that there's a non-trivial solution by the fact that this matrix is invertible because its determinant is non-zero. So we could invert the matrix, multiply by this, we would get C1, C2, C3. What else can we say about this that might be helpful to you on the test and on trying to get caught up to where we need to be in the class, since everybody neglected everything for 2 weeks to prepare for the test? Please, I understand. I knew it was going to happen. Just thinking off the top of my head, because I'm trying to get these done quickly to make them available so people can take the test this afternoon after looking at these videos. There was something else I wanted to say here, but it's lunchtime and I'm getting hungry, and apparently I can't think of it. So anyhow, another thing we can say is the same thing will happen for any matrix that we put over here. Oh yeah, I was going to say, since the matrix is invertible, then we know that these first 3 columns are going to reduce to the identity. And we're going to get a solution for C1, a solution for C2, a solution for C3. Meaning, among other things, that if W is 0, that the solution to C1 V1 plus C2 V2 plus C3 V3 equals 0 would be inverse matrix times the 0, 0, 0 column vector. The result would be 0, 0, 0. Any matrix multiplied by a column vector of zeros that's compatible for multiplication is going to give you a column of zeros. So that C1, C2, C3 would all be zeros if your W vector was the zero vector. Meaning, then, that only a trivial linear combination of C1, of V1, V2, and V3 would be equal to the zero vector, meaning that these three vectors are linearly independent. So there are all those connections that you really need to understand very well, both for the test and for what we're doing in class. So make sure we get that.